Welcome to the Problemers channel, Season 1, Episode 5, the episode in which we will discuss the solutions of the problem S1M4 and the solution of the difficult problem S1M5. As a reminder, the objective of the problem S1M4 was to find the shape and the length of a shortest circumnavigating orbit over the surface of a regular tetrahedron, which visits all four of the tetrahedron faces. The objective of the problem S1M5 was to inhale all the solutions of the problems that we solved so far, S1M2, 3, 4, and invent and solve a problem that relates to the problem S1M4 and, as a hint, has something to do with the volume of the parent regular tetrahedron. Before we deep dive into the solution of the problem S1M4, however, I would like to go quickly over the finer details of the solution of the problem S1M3. In that problem, which we solved in the previous episode, the objective was to find a shortest circumnavigating orbit over the outer surface of a cube if the original point from which the orbit is supposed to take place was located somewhere on an edge of a given cube. We solved that problem by observing that a net of a solid may have not one but several different shapes. The first shape of a net that we discovered while solving the problem S1M2 was cross-like formation, and in the problem S1M3, a winning net looked like three dominoes stacked one on top of the other and shifted by one face. Now, while we were solving that problem, we realized that the winning orbits over the surface of a cube were located or bound between the diagonals of a right and a left three faces stacked one on top of the other, as was shown in the animation that I created with a software called GeoGebra and which I captured with a software called Kazam and which we saw in the previous episode. Very well. Now, as the transform and conquer problem-solving approach prescribes, in order to obtain a solution of the original or difficult problem, we have to reverse transform a solution of the transformed or easier problem, which in case of the problem S1M3 amounted to folding our cube back into its original shape and observing the orbit that satisfies the requirements of the problem. However, when we do that, we observe that we can put together an algorithm that will allow us to solve the problem S1M3 without cutting the given cube open into a particular net. How can we do that? Well, we see that that particular orbit consists of how many legs? That's correct. That particular orbit consists of 6 legs. Each such leg passes through a given face of a cube, 1, 2, 3, 4, 5, and 6. And each such leg is parallel to a corresponding diagonal of the respective square. Consequently, when we are given a cube with, let's say, let me use the red color, the starting point, for example, here, P, then we can see that with respect to that point, we have how many diagonals? We have two diagonals, for example, for the facade of the cube. This diagonal and this diagonal. Consequently, our friendly and inquisitive ant can begin its journey going over the facade or the front face of the cube parallel to this diagonal this way or this diagonal this way. Let's say that our ant decided to go on its first leg of its orbit parallel to this diagonal. That means that first we draw a line segment that is parallel to the diagonal of the facade of the cube, like so. Then on the second leg, the orbit will be parallel to this diagonal, so it will go something like that into the point over here. Next, the third leg of this orbit will be parallel to this diagonal, and it will go something like that into this point. Now, the fourth leg of this orbit will run through the back face of the cube and parallel to diagonal that runs from here to here, like so. Now, for the fifth leg of the orbit, it will run parallel to this diagonal of the top face, like so. And on the sixth and the final leg, this orbit will run parallel to the left face of the cube, parallel to the diagonal that starts over here and terminates over here, and it will run like so. Shown with a more precise tools, such as, for example, GeoGebra, that particular orbit will look as follows. Observe that in a certain sense, this particular orbit is unique because no other orbit that runs in a similar direction but still satisfies the requirements of the problem exists. However, because this orbit is closed, it should be evident that it can be traversed in two mutually opposite directions. For example, in this direction and in this direction. Alternatively, our ant can begin its circumnavigating journey in a direction that is parallel to the second diagonal of the front face of the cube, or in this direction, like so. Let me use a different color, maybe this is supposed to be green. So on the first leg of the journey, our ant will run parallel to this diagonal until point right here. On the second leg of its orbit, the ant will run parallel to the diagonal that terminates here and begins over here for the top face of the cube, like so, unto the point over here. On the third leg of this orbit, the ant will run parallel to the diagonal that begins over here and terminates over here. Sorry, over here for the right face of the cube. It will be something like this into this point. For the fourth leg, our ant will run in a direction that is parallel to the diagonal of the back face of the cube that starts here and terminates here. It will go something like that. For the fifth leg of the circumnavigating orbit, the ant will run parallel to the diagonal of the bottom face of the cube that starts here and terminates over here. It will run something like that into here. and on the sixth and final leg of its orbit, the end will run over the left side of the cube parallel to its diagonal that starts over here and terminates over here, and in this direction it's supposed to terminate over here. Again, done slightly more precisely with the software called GeoGebra, for example, that particular orbit will look as follows. Very well. Again, because this particular orbit is closed, it should be evident that that orbit can be traversed in two mutually opposite directions, in this direction and starting in this direction. Consequently, when we take on the solution of the problem S1M4, where we asked for a similar orbit, but the one that circumnavigates not a cube but a regular tetrahedron, we also have a hunch that that particular orbit will run parallel to something. To something what? Well, again, in vacuum, taken in isolation, this particular problem has a pronounced three-dimensional flavor, and it is not really clear exactly how that circumnavigating orbit will run over the outer surface of the regular tetrahedron at hand. However, now that we know the mechanics of the transform and conquer problem-solving approach, we know that we should look for a transformation that is reversible, that preserves the technical essence of the problem at hand, and that provides a tactical advantage. It should also be evident, guys, that if you are dealing with a regular tetrahedron, then it is likely that you should experiment with putting this particular solid together from heavy or project paper, as I've done over here. This particular tetrahedron has all its faces of different colors. Consequently, if, for example, we take this point right here to be a logical top of the tetrahedron, we can we can cut this particular solid along this edge, and this edge, and open up the faces of this tetrahedron like a flower. And then, let me take the white color, one particular net of that solid will look as follows, as 4 equilateral triangles placed like so, 1, 2, 3, 4. However, with this particular net, it's not really clear. For example, let's say our point P is located somewhere over here. This is our point P. It's not really clear how the circumnavigating orbit that touches or passes through all the faces of a cube should run in such a way that it will somehow pass through all the faces and then come back to the point P. Consequently, because we fail with this particular net, it makes sense to try a different one, and a different net that is a winner in this particular case also looks as follows. I did this guy without the flaps again, so when we put this net together back into a solid, then it will look as follows, and it should be evident that we should cut for sure an edge of the given regular tetrahedron on which the point P sits. For example, let's say with this particular net, the point P is located somewhere over here. Then in this net, this edge will be split into two edges, this one, and consequently the point P will also be split into the point P, let's say P prime, over here. And if we connect these 2 points with a straight line, then that particular straight line will constitute a solution of the transformed, or easier in some sense, problem, because each and every point on that straight line runs precisely through the material of the net and does not leave the confines of this particular net. And it should be evident that the point P over here, represented by this period right here, can be located anywhere on the edge of the given tetrahedron. In order to demonstrate that particular idea, I've put together another animation with a software called GeoGebra, and I captured it with a software called Kazam. Very well. Now that we understand how this difficult problem can be solved using the transform and conquer problem-solving approach, we carefully observe that if we name the vertices of our regular tetrahedron as follows: A, B, C, for the points that delineate the base of this tetrahedron, and D as the logical top of the regular tetrahedron, then we observe that in order to produce this particular or winning net of a given solid, we cut this tetrahedron along the edges DA, DC, and AB, in which case our particular net, shown right here this way, has the following partitioning of the points. The point A, by this particular cut, is split into two, the original point A and the point A prime. Likewise, the point D is split into two distinct points, the point D and the point D prime. The points B and C do not get split at all. They remain as points B and C, and because we specifically cut our tetrahedron along the edge DA that houses the starting and the terminal point P, the point P also gets split into two copies, the point P and P prime. Now, what can we say about the solution orbit P prime in this particular case? Well, because our process of cutting a given solid into a corresponding net preserves the distances between the points, it follows that the distance from the point A to the point P will be exactly the same as the distance from the point A to the point P prime. In other words, the distance AP and the distance A prime P prime are actually one and the same distance. Likewise, the distance from the point P to the point D will be exactly the same as the distance from the point P prime to the point D prime, as depicted over here. Moreover, because not only distances but corresponding angles are preserved by our transformation, the interior angles at A, B, D, at actually all the points remain the same angles, or 60 degrees. That means that the vertical displacement of the point P, let me probably mark it like this, the vertical displacement of the point P from the line segment A prime will be exactly the same as the vertical displacement of the point P prime from the straight line A prime extended. And what does that mean? That means that the solution orbit P prime will be parallel to the line segment A prime, and likewise it can be shown that it will be, of course, parallel to the line segment D prime, as was also shown in the animation. Now, when we put together the net of this particular solid back into its original shape, so we see that the orbit closes at these points right here, this point and this point. Then again, just like with the problem S1M3 when we dealt with the cube, in this particular case we see that it becomes evident that it is possible to put together an algorithm that will allow us to solve this particular problem without cutting the given solid open into its net. In particular, our end, located at the point P, will have how many choices for the first leg of the journey? Correct. Our end will have two choices for the initial leg of the journey, because with respect to the point P, there are two opposite edges of this particular face of a regular tetrahedron, the edge DC and the edge AC. Now recall that this particular orbit will consist of how many legs? 1, 2, 3, 4. 4 legs, and each such leg will be what? Each such leg will be parallel to the corresponding edge of the given tetrahedron. That means that, for example, for the yellow orbit over the surface of the given tetrahedron, our end who departs from the point P can go parallel to the edge, for example, AC in this direction until it arrives into the point located on the edge DC, at which point our end turns the corner, so to speak, and crawls over the face DBC of a regular tetrahedron parallel to the edge DB in this direction here until it reaches the bottom of that face, at which point it turns the corner again and crawls along the base face of the tetrahedron ABC, but this time parallel to the edge CA until it arrives into point right here. Now for the final, the fourth leg of this journey, our end will crawl back up along the back face of the tetrahedron ADC in a direction that is parallel to the edge DA this way until it comes back to the point from where it departed. Again, done a little bit more precisely with the software called GeoGebra, this particular or one specific orbit will look as follows. Very well. Alternatively, our end can depart from the point P, going parallel not to the edge AC, but this time parallel to the edge DC in the downward direction right here until it arrives to a point that sits on the edge AC. Here, our end will turn the corner, so to speak, and crawl over the bottom face ABC of a given tetrahedron in a direction that is parallel to the edge AB this way until it arrives at a point that sits on the edge BC. Here the end will turn the corner again and crawl up the face DBC parallel to the tetrahedron's edge CD this way until it arrives at this point that sits on the edge DB of a given tetrahedron, and for the final and fourth leg of its orbit, the end will turn the corner and crawl over the back face of the tetrahedron ADB in the direction which is parallel to the edge AB this way, eastward, until it closes the orbit and arrives at the point P. Again, that orbit, because it's closed, just like the previous one, can be traversed in two mutually opposite directions. For example, this way and this way, clockwise and counterclockwise. Done a little bit more precisely with a software called GeoGebra, that second orbit will look as follows. And these two orbits that have the shortest possible length and circumnavigate the outer surface of a given tetrahedron in such a way that it visits all the faces of a given tetrahedron constitute the two unique solutions of the problem S1M4, and we can take on the solution of the difficult problem S1M5. Before we jump into the solution of the problem S1M5, please allow me to mention that I think in the previous segment I had that fact written on the board, but I forgot to say these words. But it should be evident from the solution of the problem S1M4 that the length of the shortest circumnavigating orbit in this case is equal to twice the length of the edge of the parent tetrahedron. In other words, the cumulative length of all four legs of this circumnavigating orbit must be 2a. Now let us address the difficult problem S1M5. Here it should be noted that a mathematical problem has two sides to it. A side of creation and the side of solution. It should also be fairly evident that each and every mathematical problem is not shipped to us wholesome from a parallel universe by superior beings. Every such problem is created by a person, and I argue that the skill, the taste, and the experience that goes into the process of creating a deep, interesting, meaningful, and crisp mathematical problem is of a higher level than the skill that goes into solving such a problem. Correspondingly, academically, it is just as, if not more important, to learn how to create mathematical problems as it is to solve these problems. However, initially, this is a very tall order. That is why here we just try a few things here and there. And if you were not able to swing the problem S1M5, then do not worry about it. This problem is very difficult and it takes certain amount of experience and skill with solving problems before that problem can be put together and solved. However, here we come across another facet of mathematics, and that is mathematics in general is full of wonderful details, and all it takes for us is to bring a shovel to the field of mathematics, begin digging, and we surely will uncover some amount of interesting information and interesting mathematical facts. Also recall that in Season 1, Episode 1, where we were discussing various definitions of mathematics, we mentioned that mathematics is not a dogma, all of whose rules are etched in stone and cannot be questioned. Quite the opposite. In mathematics, every participant is encouraged to ask questions. Consequently, as we solve problems, we should really ask questions about the details that emerge from a solution of this particular problem. Here, the reason why I gave the problem S1M5 in this particular sequence is because during the solution of the problems S1M2, S1M3, and S1M4, Potentially, we can uncover some amount of interesting details which can lead us to the creation and the solution of the problem S1M5. In particular, recall that in the problem S1M2, for a fixed pair of diametrically opposite points, we discovered a family of no less than 6 distinct paths of minimal length. However, if we concentrate on two opposite, in some sense, such paths, for example, from here to here over the front face of the cube and over the left face of the cube this way, then recall that during the solution of the problem S1M2, we actually proved that this point and this point must sit in the dead middle of the corresponding edge of the cube. In other words, this point is displaced from the corresponding vertices of the cube by exactly the same distance as this point is displaced from the corresponding vertices of the cube. That means that the line segment that connects these points must pass through the center of symmetry of a cube, O, and we should know that a cube is a centrally symmetric figure, and as a matter of fact, that central symmetry adds one element to the group of rigid symmetries of that cube. Moreover, we know that the body points that delineate a main diagonal of a cube also belong to the straight line that passes through these points, and that straight line passes through the point O. Consequently, this line segment that connects the middles of the opposite edges and this particular main diagonal intersect at the point O. Consequently, as inquisitive students of mathematics, we inquire, does this particular cross section of a cube cuts this particular cube into two solids of equal volume, and we wonder if the volume of each such solid is precisely 1/2 of the volume of the parent cube. Here we see that the length of all the legs of the shortest orbits must be the same, which means that at the minimum, that particular cross section must be a rhombus. Next, as we move on to the solution of the problem S1M3, we observe that if we place the point of origin for the orbit at hand in the dead middle of an edge of a given cube, then again recall that each of the 6 legs of this closed orbit must run parallel to the corresponding diagonal of the square at hand, and that means that if we place the point P in the dead middle of an edge of a cube, then the length of that particular leg of the orbit, for example, will be precisely 1/2 of the length of the corresponding diagonal, and all these legs will have one and the same length. Consequently, this hexagon over here, marked by this point, this point, this point, this point, this point, and this one, will be a regular hexagon, and it turns out that this hexagonal plane sits orthogonal or perpendicular to the main diagonal of a cube that runs, for example, from this point all the way to this particular point. And these two objects, this axis of rotational symmetry of a cube and this hexagonal plane of symmetry of a cube, contribute to one more type of an element to the group of symmetries of a cube called a reflective rotation, which is a single transformation that can be thought of as a combination of two more individual transformations that are combined into one transformation as follows. A rotation of a cube around this main diagonal by 2 pi over 6 radians with the consequent reflection in this plane of symmetry. But this is besides the point. In this particular case, again, as inquisitive students of mathematics, we inquire, will this hexagonal plane partition the pairing cube into two solids that have exactly the same volume, and will these solids have the volume that is exactly 1/2 of the volume of the pairing cube? Lastly, we arrive at the problem S1M4. Here again, the point of departure and arrival P can be located anywhere on an edge of a given tetrahedron. But again, as inquisitive students of mathematics, we inquire what will happen if we place that point P in the dead middle of an edge of a given tetrahedron. Then the corresponding orbit will run parallel to the respective edges of a tetrahedron, and again we will show pretty soon that the length of each such leg is one and the same. Consequently, this quadrilateral will be at a minimum a rhombus, and we inquire whether this rhombic plane will cut a given tetrahedron into two solids, each of which has the same volume, and that particular volume is 1/2 of the volume of the parent tetrahedron, and thus a problem statement for the problem S1M5 is born. We now observe that all the hunches and wishful thinking ideas that we generated in the previous segment will remain just that, hunches and wishful thinking, because the way in which mathematics works, these hunches and wishful thinking are converted or become a mathematical reality only if we are able to generate a convincing line of reasoning known as a proof that our hunch is correct, or we generate a line of reasoning which refutes that hunch and we admit that our hunch and wishful thinking were not on the money. In this particular case, however, we hypothesize, or we have a hunch, that if a given regular tetrahedron is cut along the plane that is generated by the shortest circumnavigating orbit that visits every face of a given tetrahedron and originates at the point, let's say, P, that is located in the dead middle of an edge of a given tetrahedron, then such a cut will generate two solids, this one and this one, and our thinking is that these two solids will have one and the same volume on the one hand, and on the other hand, each volume of this solid and this solid will be precisely 1/2 of the volume of the parent regular tetrahedron. In order to proceed further, we carefully name the vertices of our tetrahedron as follows: A, B, C, and D, and we name the points where the four legs of the circumnavigating orbit intersect the corresponding edges as P, Q, R, and S. In order to generate a convincing story of how and why, because remember, in Season 1, Episode 1, we mentioned precisely that mathematics is an art of telling a story, we begin our proof, or we begin our line of reasoning with a very straightforward observation with the minimal amount of details yet. For example, let's say that the point that we named S over here, that sits on the edge of the tetrahedron AC, is shown over here, and it is taken as a working assumption that the distance from the point A to the point S is the same as the distance from the point S to the point C. In other words, this distance are one and the same distance. We now claim that if we connect vertex D with the point S and the vertex B with the point S, then the resultant triangular section, cross-section DSB, will cut the parent tetrahedron into two solids of equal volume, and each such volume will be precisely 1/2 of the volume of the parent tetrahedron ABCD. In order to see that this is true, we will consider two smaller or sub-tetrahedrons, DCBS and DABS. And we want to show that these volumes are represented by one and the same number. We know that the volume of a tetrahedron is given by 1/3 of the product of the corresponding height and the area of the corresponding base. However, in this case, we know that the triangle ABC is an equilateral triangle, which means that the line segment BS is not only a median of this triangle, of that side AC, but it is also a height and a bisector of the interior angle at B. Consequently, if we consider two triangles ABS and CBS, we will see that the corresponding bases AS and SC will be of equal length, and the height of each of these triangles will be shared BS and consequently of one and the same length, which means that the area of the triangle ABS and the area of the triangle CBS is actually one and the same. Now, these two smaller tetrahedrons DABS and DCBS also share one and the same height that emanates from the vertex D, and that height I designated with the symbols H sub D and H sub D. That height will project the point D onto the plane ABC, and because of the symmetry at hand, that point will be projected somewhere on the line segment BS, but that doesn't really matter. What matters here is that the length of that height is one and the same, and consequently the volume of the smaller tetrahedron DABS will be given as 1/3 of the product of the length of the height of the tetrahedron that emanates from the vertex D and the area of the triangle ABS. But the volume of the smaller tetrahedron DCBS is also given by 1/3 of the product of the length of the same height HD that emanates from the vertex D and the area of the triangle CBS. But we just proved that these two triangles have one and the same area, which means that the volumes of the tetrahedrons at hand, DABS and DCBS, are one and the same, and we can saturate our line of reasoning with more details as follows. As we saturate our proof with more and more details, we carefully mark the points P, Q, R, and S on the corresponding edges of the given regular tetrahedron as the points where the four legs of the circumnavigating orbit around the surface of the given tetrahedron intersect the corresponding edges. Here, we suggest that the key observation for a correct and valid proof is to connect the following two points, Q and S, with a line segment like so, like so. And the moment we generate this particular line segment, it is evident in which direction our proof should go. That is, with the line segment QS, we actually generate two more, even smaller tetrahedrons in this particular case. That is, we generate a tetrahedron BQPS, and we generate a smaller tetrahedron DQRS. Consequently, if we succeed at showing that these two smaller tetrahedrons are actually equal in volume as well, then we succeed at generating a correct proof for our hunch and for our assumption, because if the volumes of these two smaller tetrahedrons are equal, since we already proved that two larger tetrahedrons that make up the parent tetrahedron have equal volumes, and each such volume represents 1/2 of the volume of the parent tetrahedron, we can account this small tetrahedron towards this shape right here, B, C, Q, R, and S. And we can account the top tetrahedron, D, Q, R, S, towards the shape over here, A, P, Q, S, D. And because these two tetrahedrons are of equal length, then we will not change the volume of the two halves that we dealt with in the previous segment. To that end, we observe that it is advantageous to treat these two smaller tetrahedrons in such a way that, for example, for the lower tetrahedron, the vertex B will be the logical top, and its logical base will be the triangle QSP. And for the top tetrahedron, its logical top will be the vertex D, and its logical base will be the triangle R, Q, and S. Here we observe, first of all, that because each face of a given regular tetrahedron is an equilateral triangle that is congruent to all the remaining ones, it is evident that the length of the line segment QP represents what? It's the middle line of the triangle ABD, and in length it's equal to 1/2 of the distance dA. But by the working assumption, every point PQRS sits in the middle of the corresponding edge, which means that all the remaining three legs of this circumnavigating orbit, Q, R, RS, and SP, also represent the midlines of the corresponding congruent triangles, which means that their lengths are one and the same. Consequently, that means that the quadrilateral PSRQ or PQRS is, at the minimum, is a rhombus. In a few minutes we'll prove that it's actually a square, but for now it doesn't matter. Right now what matters is that this quadrilateral PQRS is a rhombus, and QS, the line segment QS, plays the role of one of the diagonals of this rhombus. It is, however, well known that any actually diagonal of a rhombus cuts that rhombus into two triangles of equal areas, which means that the area of the triangle QPS, maybe if it will help, I can put a little bit of a dash line to highlight this triangle right here, is equal to the area of the triangle QRS. Consequently, we just proved that the logical bases of our smaller triangles have one and the same area. Now, because we know that the volume of a tetrahedron is given as 1/3 of the product of the length of the height on the corresponding base, we need to investigate what can we say about the length of the heights of the smaller tetrahedrons that emanate from the point B, from the vertex B, and from the vertex D correspondingly. Here it is a little bit tricky to comprehend or grasp what exactly is going on in the view where the perspective is present. That is why we can again transform this situation from 3-space into a 2-space and look at the plane PQRS in the side view as if we line up ourselves precisely, for example, with the line segments PQ and RS. So the whole rhombic plane flips into a line segment or a straight line. In that case, the edge of the given tetrahedron BD, this line segment right here, will intersect the plane PQRS at a certain angle shown over here. In theory, it is possible to compute the magnitude of that angle, but that is not where we're interested right now. Right now, of interest to us is the fact that this particular angle, which is formed by the line segment DB and the planar representation of the rhombus PQRS, let's say at the point T, represents vertical angles. In other words, the angle DT D prime and BT B prime are vertical and hence equal one another. Next, when we project the point D orthogonally on the plane PQRS and obtain the point D prime, and when we project the point B orthogonally on the plane PQRS, we obtain the point B prime. What can be said about the lengths of the line segments D, D prime, and B, B prime? Well, again, by hypothesis, we know that the distance from the point T to the point D is the same as the distance from the point T to the point B. This is basically the reflection of the fact that the point Q sits in the middle of the edge DB. However, if these two angles as vertical angles equal one another in these two triangles, and the right angles at the vertices B prime and D prime also equal one another, it means that the remaining corresponding angles in these two triangles equal one another. In other words, the angle D prime DT and B prime BT also have the same magnitude. Consequently, by angle side angle, these two triangles DT D prime and BT B prime are congruent. And in congruent triangles, the lengths of the side that lie opposite equal angles must be equal one another, which means that in this case the length of the line segment D prime is the same as the length of the line segment B prime. But these line segments represent none other than the heights of the corresponding smaller tetrahedrons that emanate from the vertices B and D correspondingly, which means that the volumes of these two tetrahedrons, according to the formula shown over here, must also equal one another. And we basically proved that if a given parent tetrahedron ABCD is cut along the plane that is generated by the shortest circumnavigating orbit that begins or originates and terminates at a point that sits in the middle of the edge of a tetrahedron and visits every face of a tetrahedron, cuts that solid into two volumes of equal length, and the volume of each such half is exactly 1/2 of the volume of the parent tetrahedron. At the end of the last episode, I also mentioned, guys, that for a top-notch job, it is a good idea to generate a solution of that problem or materialize the solution of that problem in paper, for example. Here, as a reference, I have a such model, which, when these two pieces put together, look a little funny and unnatural, but the moment we turn one with respect to the other, as if by magic, these two halves turn or generate a regular tetrahedron. And again, separately, these pieces look somewhat strange, but when they put together and turned with respect to the other, then they become, or they form, a regular tetrahedron. And here I have two more pieces that I made from the paper of two different colors. Again, when we turn one with respect to another, all of a sudden these two guys form a regular tetrahedron, and separately these guys look a little strange, like so. And the interesting part is the cross section over here, for example, on this guy and on this guy is precisely a square. Now, how can we prove that this particular cross section is not only a rhombus but a square? That is actually not too difficult to do if we observe the following. Let us concentrate on the line segment QS that plays the role of one diagonal of a rhombus PQRS. What can we say about this line segment here? Well, we already see a proof staring us in the face, so to speak, because this particular line segment QS plays the role of a median and a height and a bisector of the angle, interior angle at the vertex S of a triangle DSB, which is what? A triangle which is isosceles. In other words, in this particular case, let me grab some white. We see that, for example, the length of the segment DS is the same as the length of the segment SB. Again, why? Because in this particular case, the line segment DS plays the role of the height and the bisector of the interior angle at D of the triangle DAC, which is an equilateral triangle, and the line segment BS is actually essentially the same or similar median or a height of the triangle ABC that emanates from the point B, which means the length of the line segment BS is the same as the length of the line segment DS. Consequently, the triangle DSB, which has the edge of the tetrahedron DB as its logical base, is an isosceles triangle. Now let us concentrate on the diagonal of the rhombus PQRS that runs from the point R to the point P. This guy from P to R, from R to P. What can we say about the length of this line segment? Again, this line segment is essentially the line segment QS if we connect the point Q with the vertex B and we connect the point R, with the vertex A. In this case, what do we have? Essentially, we have the same situation that we just had. In other words, the line segment BR, in this case, BR, plays the role of what? Plays the role of the height of the triangle DCB that also emanates from the vertex B, and the line segment RA plays the role of essentially also the height or the median of the triangle ADC C that emanates from the vertex A. But we know that all the faces of a regular tetrahedron are congruent equilateral triangles, which means that the length of the line segment RB, let's put it over here, the length of the line segment RB equals the length of the line segment RA. And not only that, but these two guys have the same length as these two guys. And what does that mean? That means that the length of the line segment QS, even though it looks funny because the whole thing is in perspective, is actually one and the same as the length of the line segment PR. And now we have the following interesting situation. We have a rhombus that has the lengths of its diagonals equal. And what does a rhombus with the same or equal in length diagonals is called? Correctly, this rhombus with equal in length diagonals is called a square. Consequently, as peculiar or unnatural or perhaps strange as it sounds, the cross-section PQRS in this particular case comes out to be a perfect square. In other words, this section right here is a perfect square, and as I have shown you guys with the simple models that I have, these two halves that form a regular tetrahedron are squares. In other words, this cross section here is a square, and grab this cross section right here is also a square, and our problem S1M5 is solved. Our next challenge will consist of three problems. The problem S1M6, the problem S1M7, and the problem S1M8. The objective of the problem S1M6 is the following. We're given a regular octahedron with the edge of length A, a generic number, and we're asked to find a shortest path over the surface of that octahedron from the vertex A to the vertex C as depicted over here. Again, a regular octahedron with the edge of length A, and the objective is to find a shortest path over the outer surface of this octahedron from the vertex A to the vertex C. In the problem S1M7, we're given not a generic length, but carefully, no doubt, dialed in numbers of 20 and 7. In particular, we're given a regular tetrahedron with the edge of length 20 units of length. We're also given the median and the height DG of the face ADB right here, and we're given a height CG or the median CG of the face ABC. On these respective heights or medians, a point A and the point F is chosen in such a way that the distance from the vertex D to the point E is 7 units of length, and the distance from the vertex C to the point F is also 7 units of length as depicted over here. The objective in this problem is to find a shortest path over the outer surface of this regular tetrahedron that runs from the point E to the point F. Again, not through, not somehow out and over, but strictly over the outer surface of this regular tetrahedron. Again, I'm not going to say much more, but the fact that specific numbers are given in this problem, 20 and 7 in this case, should give us a hint of what is going on with this particular problem. Lastly, in the problem S1M8, we're given a slice or a chunk or a piece of a 3x3 chessboard, as depicted over here, with 9 squares total, with 5, let's say, black squares and 4 white squares, and we're given 4 knights of 2 colors each. 2 white knights positioned like so at the top corners of this 3x3 chessboard, and 2 black knights positioned like so at the bottom corners of the 3x3 chessboard. The objective in this problem is to swap the same colored knights with their opposites using nothing but the legal moves of a chess knight. In order to solve that problem, you do not need to know anything about chess, except that a legal move of any chess knight consists of an L-shaped trajectory. For example, this knight can only go this way and this way into this square, or this way from here to here and into this square, and likewise every other knight only allowed to follow these particular moves. For example, this white knight can jump from here this way, or from here this way, or this way. Consequently, the 2 black knights can move as follows: from here to here, or from here to here, and from here to here, or from here to here, and consequently this guy is allowed to move in the L-shaped trajectory like so: left and up, or up and left and up, or up and left. The objective again in this particular problem is to make sure that these 2 white knights are located in the lower corners over here, while these 2 black knights are located in these 2 corners of the board. Again, this problem is distinctly different from the optimization problems that we've been studying so far, and the reason I chose this optimization problems with solids because they do not really require too much specialized knowledge. But again, here we have 2 or 3 problems across which 2 sound the same, but the other one descriptively is rather different. However, as a hint, those of you who have stayed with us and followed these episodes in sequence, you guys already understand that the transform and conquer problem solving approach may help you with all 3 of these problems, and in this particular problem also a useful transformation may help. This is it for this episode. Thank you for staying with us. Thank you very much for your time. I'll see you in the next episode where we will dissect the solutions of these 3 problems.